Okay, so today we begin approximation methods, and we'll begin with the variation method, which actually has a very wide applicability uh, because it can be used to estimate the eigenenergies and eigenfunctions of many Hamiltonians that we cannot solve analytically exactly. And for our course, this will be useful in many situations, particularly for two types of problems. One where we will study the multi-electron atoms, because once we have more than one electron in the atom, we cannot solve the Schrodinger equation exactly. And we will have to use one of the approximation method. So this variation principle is one of those methods that we can use to solve for ground state and for excited state energies and eigenfunctions of multi-electron atoms. And then we can use this method also to solve for molecular orbitals and molecular energies. Of course, we usually have more than one electrons in molecules. So this method can be used to estimate the energies and eigenfunctions for molecules. And actually, more than that, we will see that this method can be used even for single particle situations where we cannot solve the problem analytically. Suppose you have one-dimensional finite quantum well. Okay, we know that for the infinite quantum well, we can solve it exactly. And you have been doing that in introductory quantum mechanics courses. But if we have a finite quantum well, and let's say the potential profile, which is given by V of x, is not, that staircase type that you can write solution of Schrodinger equation in each region and then match the boundary condition at the, wherever there is a step. If it is more complicated than that, we cannot solve it analytically exactly. So even in that situation, this method can be used to estimate the eigenenergies and eigenfunctions of this situation. So this method that we will study will actually have a very wide applicability. So, and we'll see by solving some of the examples as we go along that this method, is applicable to situation where we have only one particle, but a potential profile that we cannot solve analytically. And of course, for multi-electron particle, we cannot solve the Schrodinger equation analytically in a general situation. So that's where this method can also be used. So let me start by sharing screen. Okay. So this is chapter 8 of the book, and particularly we are going to start working the variation method for estimating the energies and eigenfunctions of a quantum mechanical problem. So let me start by working what is called the variation theorem, because this is of fundamental importance that sets the stage for us, to solve these problems. So suppose that we have, some potential, and we have, some particles in that potential, and which mean that we have a Hamiltonian specified for that problem. And our goal is that for this Hamiltonian, we want to find, let's say, the eigenfunction psi k's, which are the functions of the, let's say, the positions of the particle and we want to find the eigenenergies of this problem. For example, if you think about uh, this V as the harmonic oscillator, you have already solved it analytically exactly, that this has uh, uh, wave functions like this, and energies keep on increasing. So this has some energy E1, some E2, and so on. Similarly, if we have we can think about an atom. So there's a ground state with energy E1, then there's a first excited state with energy E2, E3, and so on. And let's imagine that we have numbered these states like this, that the ground state is psi1 and energy corresponding to it E1, and the first excited state is psi2 and energy corresponding to it E2, and energies are labeled so that E1 is the smallest, then E2 is greater than E1, then E3, and so on. So this is the labeling that we will be using. So this is the problem that we want to solve. We have psi, k, and ek, which are unknown, and we want to estimate them. And let's start first from the ground state. Later on, I will extend it to higher excited state. But for the ground state, the variation theorem state that if E1 is the ground state energy, then and you take any function phi, any well-behaved and integrable function phi, you can choose any function phi, then this thing holds, that the integral is over all the coordinates of this problem. Let's say those coordinates are d tau, and this integral phi star Hamiltonian h phi integration over the coordinates of phi, this is always equal to or greater than the ground state energy. And if phi is normalized, this is what the theorem is, but if phi is not normalized, then there is this additional term that we have to put in here to normalize phi. Then this is what the theorem says, that you choose any phi and you put in here and you compute this left side, and let me call this left side some w. So this w is always greater than or equal to E1. So just to give you an example, suppose you are dealing with a single particle in Cartesian coordinates x, y, z, then your d tau is dx dy dz, because your phi is then function of x, y, z. But if you have, let's say, two particles, then your d tau is dx1 dy1 dz1 dx2 dy2 dz2. So whatever coordinates you have in your problem, you have to integrate over all of them, and your function phi can in general have all of these dependencies. So the beauty of this method is this, that there's no restriction on phi that what it should be, as long as it's a well-behaved integrable function, that it doesn't have discontinuities or infinities in it, and it decays to zero as we go towards infinity, so that its integration is finite. So you can choose any phi, and this term that we get is always greater than the ground state energy. So it means that I can choose phi with some parameters. I can choose phi to have, let's say, parameter C1, C2, and so on. And then once I have this phi with these parameters, what I can do, I can vary these parameters C1, C2, etc., and find the minimum value of this, find these parameters where this W is minimum, because when it is minimum, its minimum value is nearest to this ground state energy. And if I'm fortunate that this minimum is equal to E1, then I will have found the true ground state. Otherwise, I will have a phi which is, closest to the ground state. So in general, you can imagine it like this, that I have C1, C2, etc. And then I have this W integral, which W is this integral over this term. So in general, when I vary these parameters, this W will vary, and maybe my ground state is somewhere here with energy E1. So at this point where this function is minimum, this is closest to the true ground state energy. And sometime, if we are lucky, we can also get a W which just touches this E1. That, and in that case, wherever this function is minimum, this is equal. This is just equal to the ground state energy. I'm going to prove this theorem a little bit later, but first I'm trying to explain how to use this theorem to find the ground state energy, and where this W is minimum, that phi is closest to the ground state wave function. Okay, so does everybody get the theorem and the method? You, Sajid?
जी सर बिल्कुल ठीक.
ओके जी, अगर बिल्कुल ठीक है तो फिर लेट्स गो अहेड एंड प्रूव दिस थ्योरम.
Sir,
जी सर.
so the shape of this expression looks very similar to the first order energy correction perturbation theory. So is there a connection there?
No, I think that is a little bit different, because in that, whatever that correction is actually added to that ground state term and function.
Okay.
Okay. Okay, so let's see the proof of this theorem. Proof is just to convince you that theorem is okay, but the main thing is about using this theorem, and that use is based on this thing, that you select a phi as general as you can, and based on your experience of ground states with some unknown parameters, and then you just evaluate this term W, and then find the parameters where W is minimum, and then at those values of parameters your phi is closer to the ground state function, and your W is closer to the ground state energy. So let's see the proof, and suppose that I have a phi, and since the psi case, we know that the psi case form a complete set. It means any function can be written in terms of the expansion of these eigenfunctions of the Hamiltonian operator. So let's say k goes from 1 to infinity in general. So this function phi, I'm writing it as an expansion in terms of the eigenfunctions. So we don't know, these eigenfunctions for every problem to write, but whatever those eigenfunctions are, I know that I can express my phi in terms of them. So if I write phi like this, then my W would be phi star h phi d tau divided by phi star phi d tau. Now let's put this phi here. So sum over k, a k star, psi k star, h. Let's call it sum over j, aj, psi j, integral over d tau, and then we have sum over k, sum over j, d tau. Okay, so when this Hamiltonian operates on this one, since these psi j's are eigenfunction of h, so h into psi j will give me ej psi j. So I can write it sum over k, sum over j, ak absolute square, because ak star into aj is ak absolute square, and then ej, and sorry, I can't write it like this because this is ak and this is aj, and similarly psi k, psi j into ej beta. Okay, and over here I have sum over k, sum over j, ak star, aj, psi k star, psi j beta. Now I can take this integral inside, and since they form an orthonormal set, these psi k and psi j, and similarly these psi k and psi j, which mean that the integral of psi k star psi j d tau can be written as delta kj, which means that this integral is 1 if k is equal to j, and integral is 0 if k is not equal to j. Whenever k and j are different, it means that these are two different eigenfunction and their integral would be 0 because of orthonormality. And when j is equal to k, then integral would be 1. Similarly here, which means that I can write this w as sum over k. Now k is equal to j because all other terms have gone to 0. So this becomes ak mod square into ej divided by sum over k ak mod square. Now so this is ek because k was equal to j. Now if you look at the top term, we have something like this: a1 mod square e1, a2 mod square e2, a3 mod square e3, and so on, divided by sum over k ak mod square. No, e2 is greater than e1, and e3 is also greater than e1 because that's how we have labeled the states. So it means that this is always equal to or greater than. If I replace this e2 with e1, e3 with e1, so I write a1 k square e1, a2 mod square e1, a3 mod square e1, and so on. So I replaced all energies with only e1. So it means that this term is now small, greater, and this is smaller because I replaced the bigger energies with smaller energies. Yes?
Sir, integral का sign ये आएगा साथ?
You integral तो खत्म हो गया ना. So the integral over these functions is equal to either 1 or 0.
और सर वो तो हमने summation cancel नहीं किया, हमारे पास दो summations थी, एक summation cancel होगी तो integral रहना नहीं चाहिए?
नहीं, वो summation बाद में cancel हुई है ना. पहले तो ये जो integral जो है ये इन पे लिया तो उसके बाद it's either 1 or 0. So when it is 1, then k is equal to j. So दो summation की जगह पे we have only one summation because the cross term, for the cross term the integral is 0 when k is not equal to j.
Okay sir, got it.
ठीक है. Okay, so over here we have ak mod square. So this is actually the key in this thing. Now this is equal to, I can take e1 common, and then I have a1 mod square, a2 mod square, a3 mod square, and so on, which is nothing but sum over k ak mod square over sum over k ak mod square, and this they cancel out, so I have this e1. So it means that this w is always equal to or greater than e1, where w was equal to the ratio of these two integrals. So when phi is already normalized, then this lower integral would be 1, and we don't have to worry about it. But usually when we start with a phi, it's not going to be in general normalized. So this is the w that we will always have to work with. So we have shown that any general phi can be used to find an upper bound on the ground state energy. Remember, this is a key to remember about this variation method, that we are not guaranteed to find ground state energy. we are only guaranteed to find the upper bound on the ground state energy, because when I have some, let's say, parameter C and I'm varying W, my W may never, reach the true ground state. But when I find the minimum value of W, I'm sure that my E1 is always less than this thing. Because of this, the W is always either greater or equal to E1. So it means whenever I have a W, I can minimize it, and wherever it is minimum, this value is always greater than or equal to the ground state energy. And how do we, can be sure that what ground state we have found is really the ground state or not? I mean, is there a way for us to learn that after solving a problem, whatever minimum W we have found, is it really equal to the ground state energy, or is it higher than that? Can anyone of you guess? Sajid?
सर सर ये मिनिमम पे तो हाईएस्ट एनर्जी होगी ना?
हाईएस्ट मतलब?
मतलब ग्रेटर मतलब डब्ल्यू की जो वैल्यू है वो सर जब इसका आर्ग्यूमेंट जब मिनिमम होगा सर, बल्कि इसकी वैल्यू मिनिमम होगी ये जो बॉटम पॉइंट
मेरा सवाल ये है कि जब हम W को मिनिमाइज करेंगे और एक मिनिमम W फाइंड करेंगे, अब वो या तो ग्राउंड स्टेट एनर्जी के बराबर है या उससे ज्यादा है, तो इज देयर अ वे टू नो दैट व्हाट वी हैव फाउंड इज रियली अ ग्राउंड स्टेट एनर्जी, और इज इट हायर देन दैट?
अगर मिनिमम होगी तो वो ऑलमोस्ट इक्वल टू ग्राउंड स्टेट एनर्जी होगी सर।
नहीं, लेकिन हमें ग्राउंड स्टेट का तो पता ही नहीं, अगर पहले ही पता होता तो फिर तो प्रॉब्लम सॉल्व करने की जरूरत ही नहीं है।
हाँ जी सर।
हमें तो सिर्फ W का पता है और मिनिमम W, हम ये तो थ्योरम हमें बता रहा है ना कि दिस W इज ऑलवेज गोइंग टू बी इक्वल और ग्रेटर देन E1, बट वंस वी हैव अ W which is minimum and we know the parameters where it is minimum, is there a way to check if this is really the ground state or if it is more than that?
सर हम श्रोडिंगर इक्वेशन में डाल के देख लेंगे कि वो सैटिस्फाई।
बिल्कुल। किसको हम डालेंगे भला?
सर W को
नहीं, W को नहीं, फाई को डालेंगे। W तो वो इंटीग्रल है ना, और जहां पे W मिनिमम होगा वहां पे हमें वो जो पैरामीटर C1 C2 एटसेट्रा वो मिल जाएंगे। इसका मतलब है वी नाउ हैव फाउंड अ फाई। ठीक है, सो ये जो फाई है जिसमें इनिशियली ये पैरामीटर थे, अब हमें एक नया फाई मिल गया है क्योंकि हमें ये पैरामीटर मिल गए हैं, एंड वी हैव दिस फाई। नाउ व्हाट वी कैन डू, वी कैन पुट दिस फाई इन द श्रोडिंगर इक्वेशन एंड चेक if we get an eigen function type equation multiplied with some energy. So it means if this is an eigen function of H, now जब हमें ये साबित हो जाएगा कि this is an eigen function of H, there is only one of the possibilities, one of these possibilities, and that is that either this is the ground state, or maybe this is first excited state, or maybe this is second excited, and so on. So अगर इसको satisfy करता है तो we can now be sure that phi minimum is equal to either psi 1 or psi 2 or psi 3 and so on. So and then by looking at other properties of phi, we can be sure that if it's a ground state or not. For example, most of the potential that we work with, they have an even parity, that they are symmetric around X, which means that the ground state will also be symmetric around X. And generally, that ground state comes without any node, and then the first excited state come with one node, and then second excited state will come with two nodes, and so on. So if it is a function which satisfies this equation and it doesn't have any node, it's most likely the ground state function, and your energy is the ground state energy. But in general, there's no way for us to know if our W is really equal to ground state energy or if it is just an upper bound. And that's an important thing to keep in mind, that we have to use the physics of the problem to be able to see that what we have got is, really an eigenfunction or not. Let's start with an example to understand this, method. Okay. Suppose I have one-dimensional harmonic oscillator. Okay, and suppose that its potential profile is given by half ax square, or I can also write it half omega square mx square. And if I write omega as 2 pi nu square, where nu is frequency, so I can write it as 2 pi square nu m x square. So this is my potential of this one-dimensional harmonic oscillator. And suppose that instead of solving the Schrodinger equation and finding the ground state from there, which we already actually know because we know that this problem can be solved analytically anyway. But just to show how the method works, we are going to use this method to find the ground state energy and the ground state wave function of the one-dimensional harmonic oscillator. And we are taking this problem simply because we already know the solution. So the method will convince us that this indeed is, the method that works. So, and since we know, that this is a symmetric wave function, it means that our ground state wave function will also be symmetric. And the ground state, usually has this form. So based on this experience, we can assume a ground state wave function like this. And let me put some parameter n here, just for the sake of normalization. So I'm starting this function with this unknown parameter c and unknown parameter n. This n, we can always find by requiring this phi to be normalized. But the main thing is going to be this c, that how to find this c such that our W is minimum. I'm choosing this particular form for phi because I already know the solution. In general, when you start choosing this function, there's no way for you to say that, okay, this should be a better choice than somebody else. So there are many ways of choosing better and better estimate, and we'll talk about them later on. So for now, let's start with this wave function. So it means W would be phi star Hamiltonian phi, and d tau this time is just dx, and my integration limits are going to be minus infinity to infinity. And then over here I will have phi star phi dx like this. So this integral, let me actually do both of them one by one. So let's start with this one first, phi star, and Hamiltonian in this case is minus h cut square over 2m dx square d square dx plus 2 pi square nu m. Should have put a square here, right? Because this was a square. Nu square m x square into, so there's an n mod square, let me get it out, and exponential, you can put exponential minus c x square here and exponential minus c x square here dx. So this is the top term. So n square and e minus c x square minus h square 2m d square dx square minus cx square plus 2 pi square nu square m x square exponential minus cx square dx. There's a dx square, and this n square is multiplying everything. Okay, so I get n square. We have to operate this one. Minus h square over 2m can be taken out, minus cx square. So when I operate the first derivative, it would be minus 2cx exponential minus cx square dx and plus this, the last term. And then we operate with this derivative again, and exponential minus cx square and minus 2c minus cx square, because x derivative is 1 and this comes as it is, then we get plus 4c square x square exponential minus cx square dx square plus this term. And then I can combine these terms. So this would be minus 2c exponential minus 2cx square. The next one is 4c square x square exponential minus 2cx square. And there's this last one. So you can find these integrals in any standard text. This is a simple Gaussian integral. This is Gaussian integral with x square. And similarly, the last term is with x square. And the final answer is something that I can write, and it is h square m pi c 8 half plus nu square m pi 5 8 power half c minus 3 by 2. And this integral phi star into phi, which was in the bottom, this similarly can be found as n square pi 2c half. And by requiring it to be 1, I can actually compute this n mod as 2c over pi 1/4. And then if I use now this integral, so the w becomes what you have to do is divide this term by this thing, and w will be h cut square c over 2m plus pi square nu square m over 2c. So this is what w is. And now all we have to do is find the value of c where this w is minimum. And how we can do that? We can, take the derivative of w with respect to c and put it equal to 0. And the derivative of c with respect to 0 of this function is h square over 2m. Derivative of c is 1. And derivative of 1 over c is minus pi square nu square m over 2c square, and let's put it equal to 0. And this will, let's take this term over there, and we get c is equal to pi mu m over h cut plus minus. Okay, because this is c square, at the end I'll have to take square root, so I'll get plus minus. Now our function was of this form, n exponential minus c x square. And if I take this c to be negative, so this minus into minus would be plus, and our function would be something like this. So phi would be something like this, because it would become some positive number. जी साजिद,
सर ये वैल्यूज जो प्लग इन की हैं इनको एक दफा रिपीट करेंगे सर?
कौन सी वैल्यूज?
ऊपर जो टोटल वैल्यूज प्लग इन की हैं, ये w इज इक्वल टू h काट स्क्वायर, ये फाइनल वैल्यू जो बनाई है w की।
हाँ, ये देखे ना, ये जो है ना, ये है ये वाला इंटीग्रल 5 स्टार h 5 स्टार dx। तो इसको इससे डिवाइड करें तो ये आ जाता है।
एग्जैक्टली सर।
हाँ जी,
ठीक है सर, थैंक यू।
ठीक है।
थैंक यू।
You can work out the algebra if if you have doubt.
All right sir, thank you.
Okay, perfect. So this is done. So everybody understand this method, that if you have a parameter in a function and you want to find where what's the value of the parameter, where your function is minimum or maximum for that matter, you take a derivative and put it equal to 0, and we see that we will get two values, and you can actually check that for both of these values it's a minimum, but we cannot select this plus value, because if we choose plus, our wave function phi of x will grow as x increases in plus or minus direction, which means that this is not a physically reasonable choice. So I'm sorry. So this positive c is a reasonable choice, but the negative c is not a reasonable choice, because there's a negative sign already here that I have used. So what we can do is choose a c with pi nu m over h cut value. So with c is equal to pi nu m over h cut, our w is minimum. And now we also have to find the value of the w at this c. So when I compute this w, so what you do, you put this c back in here, and here, and compute this w, and you can work it out, and the answer comes out to be half h nu, which we already know is actually the ground state energy of the one-dimensional harmonic oscillator. Okay, and if we didn't know what the energy of ground state of the one-dimensional Hamiltonian is, we will actually have to just assume that this is an upper bound on the ground state energy. So is everybody okay with the application of this method and how to use it?
Yes sir.
Perfect. So is there any questions? Zara, you have a question?
Yes sir. सर इसमें तो हमने इनिशियल जो अपना वेव फंक्शन था वो हमने गेस कर लिया था, तो हमें पहले से पता भी था. So if you have a Hamiltonian जिसका हमें नहीं पता, how do we go about that?
जी, तो उसमें you can start with the wave function form. For example, let's think about a one-dimensional a potential box. So a potential box has let me share screen. So a finite potential box like this has solutions like this. Okay, so it means that I should choose a function first of all, which is decaying away from center, and it's symmetric. If this is my x is equal to 0, it is symmetric. So for example, and when it reaches a certain point, let's call it some x is equal to minus a, and this is x is equal to a. If there's a finite potential, it shouldn't go to 0. It should be some small value. So for example, if I choose something like this. I see that when x is equal to minus a, so first of all, at x is equal to 0, I get a number which is at x is minus c square. So it is somewhere here, which means first of all that my c has to have some iota in it, but that's okay. And as we increase the value of c, increase the value of x, when x increases, this number increases, and this number increases. So this actually this probably may not work. For this will become x square minus c square. Yes, so when x increases, then this is a constant. So it doesn't matter if x increases this way or this way, because of this square, this function is going to decrease. So this is also a sort of a good candidate for this. And actually, even for this potential, you can also assume it to be something like this, or maybe we can construct some cosine, sine function, etc. So in general, there's no specific rule that this is how we should choose. But in the next lecture, we will come up with a way that will give us a sort of a rigorous way of choosing these parameters when we want to have more than one parameter, that we actually choose a distribution of this function in terms of some orthogonal set. For example, you choose your parameters to be many more than one, and then you choose these 5 cases to be from a set of complete function. For example, अगर आप कोई भी एक सेट ले लें जिसके जो फंक्शंस हैं, दे फॉर्म अ कंप्लीट सेट. फॉर एग्जांपल जो कोसाइन और साइन के फंक्शन हैं, they also form a complete set. Any other function can be represented in terms of that, any periodic function. Or इसी तरह in terms of integral, we can express other functions. Or we can, let's say, also choose spherical harmonics to represent any function of theta phi. Even though the trouble is that we will have to use infinite number of them in general, but once we choose the representation of the function in terms of a function like this, where we express the function as a superposition of these orthogonal functions, then if you use this phi, then this is a systematic way of finding the values of parameter. But then of course we will have more than one parameters to work with. Okay, but when right now, since we are just beginning, we are trying to find functions that only depend on one parameter.
Right. Thank you.
Okay, actually, I think let's go for a quiz today, and let's just use this thing for the quiz. So the quiz is that, let's say you have a finite potential well, and it is situated from x is equal to minus a to plus a, and it has a potential 0 inside the well and potential v naught outside the well. And let me give you the trial function myself. Let's say the trial function is something like this. This a is the normalization constant, and this c square is the parameter that you have to find. So estimate the ground state energy of this well. So essentially you have to find this parameter c in terms of a and in terms of v naught. So once you're done, you can take its snapshot and upload to LMS. I'm going to create a reception at LMS.
सर ये इन्फिनिट पोटेंशियल वेल है ना?
यानी ये फाइनाइट पोटेंशियल वेल है। सो ये -a से a तक 0 है पोटेंशियल, और फिर इधर से इधर ये v0 पोटेंशियल है, ये इन्फिनिट नहीं है।
तो सर हम पोटेंशियल की जगह वी नॉट ले लें?
नहीं नहीं, आपने उसके दो पार्ट्स बनाने होंगे, इस रीजन के अंदर 0 है और इधर इधर v0 है।
ओके सर।
बाय द वे, नेक्स्ट वीक जो हमारी क्लास है वो क्लासरूम में होगी। सो आप सब लोग प्लीज जो है वो क्लासरूम में आ जाएगा, अपनी जम्बील से क्लासरूम का नंबर देख लें।
सर अभी तक लम्स की तरफ से कोई ऐसी मेल
आई एम एक्सपेक्टिंग एन ईमेल मे बी टुडे और टुमारो एट मोस्ट।
ओके सर।
अगर नहीं आती, अगर लम्स अनाउंस करती है कि वो नेक्स्ट वीक भी क्लोज है या कुछ और है, तो देन ऑफ कोर्स वी विल कंटिन्यू लाइक दिस, बट माय गेस इज दैट द ईमेल शुड बी कमिंग टुनाइट।
सर,
जी
फिर ये जो क्लास नोट्स हैं इनका पीडीएफ बना के अभी अपलोड कर सकते हैं आप एलएमएस पे?
जी जी, मैं कर,
साथ हम देख लेंगे थोड़ा।
हाँ जी हाँ। So, मैंने अपलोड कर दिया रिसोर्सेज।
सर
जी जी,
फिर ये लिमिट से हम लोग 0 से -a लेंगे या ये लिमिट्स की सर समझ नहीं आ रही है। ये फाइनल
माइनस
लिमिट्स बता
इन्फिनिटी से -a तक और फिर -a से a तक और फिर a से इन्फिनिटी, इस तरह से लिमिट रखेंगे तो फिर ये होगा।
हाँ, -a से इंफिनिटी तक सर।
नहीं, माइनस इन्फिनिटी से -a तक और
जी
फिर
सर।
-a से a तक और फिर a से इन्फिनिटी तक।
ऑलराइट, थैंक यू सर।
हाँ सर।
जी जी।
सर ये फंक्शन तो ब्लो अप नहीं कर जाएगा न्यूमरेटर में जब हम माइनस इन्फिनिटी टू इन्फिनिटी साई मॉड्यूलस स्क्वायर डीएक्स करते हैं?
सही कह रही हैं। क्योंकि when x goes to plus minus infinity, it will blow up.
तो सर फिर हमारी डिनोमिनेटर की टर्म तो इन्फिनिटी पे चली जाएगी ना फॉर
नहीं,
डब्ल्यू।
अब ये असल में सारा ही फिर मसला खराब हो जाएगा, क्योंकि ये फाइ जो है ना, ये उस चीज पे पूरा नहीं उतरता जो हमने कहा था कि इट शुड बी अ वेल बिहेव्ड इंटेग्रेबल फंक्शन.
जी सर।
Let me give you another possibility for this function. So actually, then what we can do is make this problem little bit simpler. Let me say that this function phi is like this. That from minus c to c, it's given by this. And after that, it is 0. So what you do that instead of integrating from minus infinity to minus a, you just integrate from minus c to minus a, and minus a to a, and a to c. Okay, imagining that this c is greater than a, and that's usually it happens that after a while our function goes to 0. Okay, so don't integrate it from minus infinity to minus a, integrate it from minus c to minus a, and on this side integrate it from a to c.
सर ये जो दोनों कांस्टेंट्स हम सी यूज कर रहे हैं दोनों सेम हैं जो फाइ में है और जो आपने भी लेबल किया?
नहीं, हाँ बिल्कुल ये c सेम है. So this c and this c is actually the same. Okay, so use this phi. That this is the phi only from minus c to c, and before minus c and after c, phi is 0. So actually what I can do is that I can increase the submission time so that you can work it out at your leisure, and maybe you can submit it by 8 or 9 p.m. Is that okay?
सर कितने बजे तक?
9 बजे तक कर दो.
सर मैं
सर
सर मेरे से गलती से दोबारा सबमिट हो गया तो मैं दोबारा अपलोड कर सकती हूँ ना दोबारा करके?
मैं enable कर दूंगा, अगर मसला हुआ तो आप मुझे ना ईमेल पे भेज दीजिएगा।
चलें ठीक है, ओके, थैंक यू सर।
सर ये पोटेंशियल का जरा कंफर्म कर दें कि ऊपर वी नॉट है और वेल के अंदर 0 है ना?
जी जी, वेल के अंदर पोटेंशियल 0 है और वेल के बाहर पोटेंशियल V नॉट है।
ठीक है सर।
ठीक है, let me upload this corrected notes on LMS as well. Okay, I hope that there won't be any other issue.
सर
जी जी,
सर ये तो फिर काफ़ी सिंपल हो जाएगा, मतलब -c से a तक पहले हम इंटेग्रल ले लेंगे
जी जी,
और फिर a से c तक जो है इंटेग्रल लेकर ऐड अप कर देंगे
जी जी,
न्यूमरेटर में, और सेम ट्रीटमेंट डिनोमिनेटर में करेंगे
बिल्कुल, लेकिन
w के लिए।
न्यूमरेटर में साथ पहले हैमिल्टोनियन भी अप्लाई करना है।
एग्जैक्टली सर, एग्जैक्टली हैमिल्टोनियन, फिर वो श्रोडिंगर वेव इक्वेशन के मुताबिक जो है वो एनर्जी में कन्वर्ट हो जाएगा।
नहीं नहीं, एनर्जी में नहीं, वो पूरी इक्वेशन ही लगानी, सिर्फ हैमिल्टोनियन अप्लाई करना।
जी सर। नहीं सर, वो जैसे एग्जांपल में किया है हमने,
हाँ
उसमें
बिल्कुल,
हमने।
जैसे बिल्कुल बिल्कुल।
जी सर, थैंक यू सर।
ओके, ओके जी, अल्लाह हाफिज।
अल्लाह हाफिज़।